Video on section 5.5, the trapezoidal rule. So we'll start with the PDF. And this is the area of a trapezoid. Ready? A trapezoid is a quadrilateral with one pair of opposite parallel sides. So in the trapezoids we're going to deal with today, the bases are going to be the sides that are perpendicular to the x-axis. The height is going to be along the x-axis. That's going to be your delta x. So what's happening here is if you average these two bases and you multiply that average times the height, you've in effect created a rectangle which would have the same area as the trapezoid. Okay? So for the area of the trapezoid, multiple trapezoids for the approximation, delta x is the height. This 2 represents the averaging what's inside the parentheses. So if we just write it this way, the delta x is the h. This 2 represents the average of these two heights. Well, two heights. This is the height, which is along the x-axis, and these are the two bases. So it would bring you to this, which is, and if you notice in this expansion, these interior bases are shared by multiple trapezoids. It is only the leftmost and rightmost bases that are in here once. Everything else is shared by two trapezoids, so we can count it twice. And the trapezoidal area is, in effect, it's the average of LRAM and RRAM. Okay, so worst case scenario, you get confused by this. We're working on the AP test. You could do twice as much work and calculate LRAM and RRAM and take their average, and you would get the trapezoidal approximation. So we're going to go to the PowerPoint. And here is an example, which is not in the book. So you have this quadratic, and you want to approximate the area under the quadratic from 0 to 4. The actual area, you would anti-differentiate this. You would get 20/3. That's the exact area. But if we want to just use this curve to practice the approximations, here's our LRAM approximation. And if you notice in LRAM, these are all rectangles because you have two pair of opposite parallel sides. When we get to the trapezoids, only these vertical sides will be parallel. Where you're hitting the curve will not be parallel to the x-axis. So LRAM underestimates the area of the curve. RRAM. So if you look at LRAM, what are you doing? The left edge, the left input is hitting the curve, and you're boxing it off to the right. We go to RRAM, the right input is hitting the curve, and you're boxing it off toward the left. And the RRAM approximation is too high, and their average would be the trapezoidal approximation. And here's what that looks like. So we just look at the one trapezoid. Ready? You're going from the x-axis up to 1. You're going to the x-axis. And what are you doing to the input of 1? You are squaring that and adding 1/8 to it. Oh, I'm sorry, you're squaring it, multiplying by 1/8. Okay, so you're getting 1 plus 9/8. And the average of those, you multiply that by 1/2. Well, what they didn't show here is that the height of this trapezoid is your delta x, it's a 1. Well, they didn't have to show it because it's the identity element multiplication, but that's how you're getting these individual areas for these specific trapezoids. Well, the 1/2 can be factored out front, and then you notice that all these interior bases are shared by two trapezoids. giving us this algorithm. Ready? The H is delta X. This 2 has been factored from inside the parentheses because you are averaging these sums to get the average of the bases. The leftmost endpoint counts once, the rightmost endpoint counts once, and all the interior endpoints are counted twice because they're shared by 2 trapezoids. So back to the PDF. What you want to do is use what was on the PowerPoint as your model to do problem 3. So example 1 in the textbook doesn't map on to the example in the PowerPoint, but it's the same idea. They're both quadratics. Okay, so either go to example 1 in your book and use that as your model to do problem 3, or just back up to the PowerPoint again and look at the example of the quadratic on the PowerPoint. Okay. So example 3 is this. You want to approximate the area under x cubed from 0 to 2. And they specify you want 4 intervals. So if you want 4 intervals from 0 to 2, delta x would be a half. Okay? So here's your delta x, 1/2 there. And then this 2 has been factored out from averaging those bases. So the first input would be a 0. Put 0 in the function, you cube it. The next input's 1/2. Put it in the function, you cube it. Next input's 1. Put it in the function, you cube it. Next input's 3/2. Put it in the function, you cube it. And then your last input's 2. You cube it. And this interior ones get doubled. So that takes you to an approximate area under the curve using the trapezoidal approximation of 4 and 2,500 square units. These 7 screens are the graph length using areas by Josiah. So here's the picture. Here's Josiah's 4 and 2,500s, and here's the actual anti-differentiation, which gives you a 4. Below here, you can see using the RAM program, you get LRAM, here's RRAM, and their average is the trapezoidal approximation. Okay? So example 2 in the book, instead of giving you a function, just gives you a data set. And that's on page 308. And then they ask for the average value of that function. But if you look at example 2 on page 308, you count the endpoints, which are 63 and 55 once, the interior points twice. The delta x in this case is 1. So you distribute a 1/2 over everything, and then the average value you divide by the width, which is 12, take away 0. So you get the total area, which is 782, and the average area, which is 782 over 12. So that's your model to go and do problem number 7. So you're going to pause this video to do 7, and we'll pick up from there. So here's 7. Right? We're going to do this like example 2 in the book. So these are your dependent values. The 12 gets counted once, the 18 gets counted once, and all the interior heights get counted twice because they're shared by 2 trapezoids. In this case, your delta x is 1. So you have 1 in the numerator. This 2 has been factored out because you average the bases. And it would take you to 74 square units as an approximate area covered by the data in the table. And they didn't ask you for this, but the average value of the function would be 74/6 to match up with the way it was done in example 2. Okay? Now, from the questions at the end, ready, this is problem 33 from the standardized test questions. Use 8 equal subdivisions from 2 to 12. They're just telling the LRAM answer. So LRAM answer for this function is 16 and 6/10, and the trapezoidal approximation is 16 and 4/10. What must RRAM be? You can pause this as you work that out, and you would get 2 minutes for this question in May, but you should be able to do this faster than that. So when you're ready, well, we know the trapezoidal approximation is the average of LRAM and RRAM. So what was given was 16 and 6/10. What's missing is RRAM. Divided by 2 equals 16 and 4/10. Clear the fraction, add a negative 16 and 6/10 to both sides, and you get 16 and 2/10. Which, if that's RRAM, that averages with 16 and 6/10 to give you the trapezoidal approximation of 16 and 4/10. Okay? So, this picture is from Melanie Galantino, where she drew this to help you understand why the average of LRAM and RRAM is the trapezoidal approximation and not equal to MRAM. So in the picture, you can see the reason this does work for the trapezoidal approximation is because it's the average of the outputs, the heights, whereas MRAM is based on the input. So the input is halfway between these two, but the output, because you have a curve, unless it was a linear function, the output's not going to be between those two outputs. Okay, and additionally, here is a picture for an increasing or decreasing function where LRAM is in orange and RRAM is in green, about what overestimates and what underestimates the function. And then does the trapezoidal rule overestimate or underestimate it? It depends upon the concavity. So if the graph is concave up, the trapezoidal rule will overestimate it. If it's concave down, the trapezoidal rule would underestimate the area under the curve. Okay? So that's it for 5-5.